In this video, we are going to talk about the wave equation motivated by vibrations on an elastic string. This is the first of my overview slides, and this is the second of my overview slides. In this video, we are going to look at the wave equation, and we are going to use vibrations on an elastic string to motivate the wave equation. So suppose we have an elastic string of length L, tightly stretched between two supports at the same horizontal level, so that the x-axis lies along the string. And here's our picture. This is x equals 0, and then L distance away, we have our string, and it's stretched out at this x equals 0, and so that's this dotted line here. And our x-axis is along the length of the string. So suppose the string is set in motion so that it vibrates in a vertical plane. So now it's set in motion, and we have this vibration at some point t, and it looks like this blue wave. Let u of xt denote the vertical displacement experienced by the string at point x at time t. So here, for example, at this time t, whatever time this blue curve represents, we can look over here at this value of x and see this vertical displacement u of xt. So you can see that the displacement depends both on time and also on the distance from x equals 0. If damping effects such as air resistance are neglected and amplitude of the motion is not too large, then u of xt satisfies the second order differential equation, a squared second derivative of u with respect to x is equal to second partial derivative of u with respect to t. And here I've rewritten the wave equation, and x can go between 0 and L. The time is always greater than 0, and a squared is equal to t over p, where t is equal to tension, rho is equal to the mass over length, or mass density. And we can see that the units for a squared tells us that a is a velocity. And looking at our wave equation, our a squared u partial derivative with respect second partial derivative with respect to x is equal to u second partial derivative with respect to t for x between 0 and L, t greater than 0. We have these boundary values, that is, at x equals 0 and x equals L, our string is fixed. So its position is equal to u. So u of 0t and u of lt is equal to 0. That's our boundary values. And again, that reflects the fact that the ends of the elastic are fixed. Then we also have u of x0. So at time equals 0, we have our initial position, which is equal to f of x. We can also look at the first derivative of u with respect to t, and that will give us our initial velocity, and we'll set that equal to g of x. So at time equals 0, we have our first derivative, which is velocity, and that's g of x. And while we motivate our discussions by looking at vibrations on elastic strings, the wave equation is a general equation that governs transverse waves, such as water waves and acoustics waves, electromagnetic waves in the atmosphere, and elastic waves in a solid body. This is the two-dimensional wave equation here. Here we are only concerned with u of x. X is our one dimension. If we had two dimensions, x and y, we have a two-dimensional wave equation, and we have a three-dimensional wave equation. We could spend time deriving this wave equation, but I'm not going to do that. It is derived for you in the appendix of your book. What we will do is come up with a solution for the wave equation. The first case we will look at is an elastic string with non-zero initial displacement and 0 velocity. So now our initial displacement at time t equals 0 is equal to a function f of x that is non-zero. It is true that f at x equals 0 and f at L equals 0 will be 0 because the string is fixed. And then also, just to note, our velocity, which is u first derivative with respect to t, is equal to 0. So our initial velocity is 0 in this case here. Next, we'll look at the elastic string with non-zero initial velocity. So in this case, we're going to let our f of x, our u of x0, our initial position be equal to 0, but now we'll let our first derivative of u with respect to t, be given by g of x. So that's our initial velocity at a point x. And this is what our solution will look like. And then last, we'll look at the general problem for the elastic string, where we can have a non-zero initial displacement and a non-zero initial velocity. And what we find is we can solve this using superposition of these two solutions and simply add these two solutions to get the solution for the general problem. But first we're going to back up and we're going to solve for the elastic string with non-zero initial displacement. Looking at the elastic string with non-zero initial displacement, so the string is disturbed from its equilibrium position and released at t equals 0 with zero velocity and then is allowed to vibrate freely. So the vertical displacement satisfies our second order wave equation. Again, our string is fixed at x equals 0 and x equals L, and it's fixed at 0. So u of 0t and u of lt is equal to 0. Again, this is about the string being fixed on the boundaries. Then we also have that our position u of x at time t is equal to a function f of x. So again, we disturb the string at time t, but how much it's disturbed depends on x. So that's our function f of x. This is when we disturb the string or disturb it from its equilibrium position at time t equals 0. And then we have no velocity, so our first derivative with respect to t, which is velocity, at t equals 0 is equal to 0. No initial velocity, just a little disturbance. And then looking at these, just to kind of write these out, which you can get from these conditions here. So u of x0 equals f of x. So this is our initial position. Our first derivative with respect to t is going to be g of x. That's our initial velocity. So again, f of x and g of x denote our initial position of velocity. And f of 0, again, now we're just looking at the position as a function of x at time t equals 0. F of 0 and f of L is equal to 0. Those are our boundary conditions. And g of 0 and g of L is equal to 0. Again, there's no initial velocity. And this is an overview of what we are going to do. So I outlined all the steps, and actually these steps will look very familiar if you did the heat conduction unit or video. So first we're going to assume the solution u of xt is a product of two functions, one depending only on x, so that's our function capital X, and the other function depending only on temperature time, that's capital T. So u of x is the product of these two functions. Then we can take our second partial derivative with respect to x, that's x double prime of t, our u double prime of t then, and we can substitute it into our wave equation. Then much like we did for heat conduction, and actually we're going to go over each of these steps in more detail, but I just want to give you an overview. So just like heat conduction, we're going to use the method of separation of variables. So I'm going to gather all my x variables on one side, all my time variables on the other, and we'll see that it's going to be equal to a constant. And when we can separate this out and we'll get two ordinary differential equations, one with boundary conditions and one with initial conditions. So first we're going to solve our first ordinary differential equation of x, and again it has boundary conditions. And then we're going to solve our time ordinary differential equation. It will give us a fundamental set of solutions. So the general solution is a linear combination of our fundamental set of solutions, and then we're going to use the initial condition here to solve the initial value problem to find our coefficients. But what we will find is our coefficients is the Fourier sine series of f of x, because f of x is our initial position, and then this will be our final solution to our equation. Again, this whole method here is very similar to heat conduction because of the first assumption that our solution is a product of two functions and the fact that we use method of separation of variables. And now we're going to back up and look at each step in a little more detail. And also I told you this will look very familiar if you've done the heat conduction. There is a little difference, so it's not exactly the same. So it is worth going through the derivation. But we will start by assuming the solution u of xt. Remember, u is this displacement and it depends both on position where we are on the string, and time. So we're going to assume u of xt is a product of capital X, which depends only on position, and capital T, which depends only on time. Then we could take the second order derivative of u, the second partial derivative with respect to x, so that'll give us x double prime times t. And the second derivative with respect to t is going to be x times t double prime. So when we plug these two values here into our equation, the wave equation, what we will get is a squared x double prime t is equal to x t double prime. And then we use the method of separation of variables to find non-trivial solutions when f of x is not equal to 0. So we take this equation and we want to isolate x on one side and t on the other. So we'll start by dividing this equation, both sides of the equation, by x. Is that right? Yeah, x, so that we can get the x, rid of x on this right-hand side of the equation. And we'll get x double prime, and then also we divide both sides of the equation by a squared t, so we can get rid of this t. So we have x double prime x is equal to 1 over a squared t double prime t. And this here is equal to some constant then, minus lambda. So if I look at this equation, x double prime x equals minus lambda, that's equivalent to x double prime plus lambda x equals 0. And when I look at the 1 over a squared t double prime over t is equal to minus lambda, that's equivalent to this equation here, t double prime plus a squared lambda t equals 0. So what we have seen is these two equations here then are two ordinary differential equations. We have transformed our second order partial differential equation to second order ordinary differential equations. Ordinary being not partial derivatives, but just, well, there's only one variable, so derivatives. And then looking at this, I'll look at x, my x function, and what we do have is that x of 0 and x of L is equal to 0. We have these boundary values that on the boundary x is fixed. So this is our boundary value problem. And we also said that the derivative of t, right, there's 0 velocity, initial velocity, so t prime of 0 is equal to 0. And this means that t has an initial value. Looking at the boundary value problem, we have x double prime plus lambda x equals 0, subject to our boundary values. And this is an eigenvalue problem, and in fact, it's the same eigenvalue problem as the heat diffusion. And in case you need a refresher on how we solve this eigenvalue problem, we started by letting our eigenvalue is equal to mu squared, so we wouldn't have to deal with square roots and things. So letting lambda equals mu squared, we have x double prime plus mu squared x equals 0. Our characteristic equation for this is equal to r squared plus mu squared equals 0. So that tells us r is equal to plus or minus mu I, which gives us the general solution to this equation, characteristic equation, is c1 cosine of mu x plus c2 sine of mu x. To solve for our constant c1 and c2, we're going to plug in our boundary conditions. But our boundary conditions in our problem statement is in terms of u. However, our differential equation here is in terms of x. I did write the boundary values here in terms of x, but I had calculated it before, and I gave this to you without showing you how this was done. And you can kind of intuitively think that this is the right answer, but here is how you would formally take the boundary values you have from your problem in terms of u and get your boundary values for x, so you can solve this boundary value problem here in terms of x. So u is equal to x times t, function x times function t. And when x is equal to 0, u is equal to 0. So I'm going to plug in x, position x equals 0. So 0 for x. Now this is equal to 0, but since time is not equal to 0, that must mean x of 0 is equal to 0. So this is our first boundary value, or our first boundary condition for our ordinary differential equation. Similarly, we know that position u, L of t is equal to 0 because it's bounded here, it's fixed. So we plug in x equals L and t equals some time t. But since time is never equal to 0, that must mean our x of L function is equal to 0. So this is how we get our second boundary condition for our ordinary differential equation of x. Now that I have these two boundary conditions, I can plug them in to my formula. So y is a solution for x. So that means if I plug in 0 into here, I am going to get, using x of 0 is equal to 0, I get c1 times cosine of 0, which is equal to 1, plus c2 sine of 0, which is equal to 0. So I have c1 is equal to 0. Now I can plug in xl equals 0. So plugging in L here, except C1 is equal to 0, so this is automatically 0. And now I have C2 sine of mu L. So that means mu L is equal to n pi, which means that mu is equal to n pi over L, which means lambda is equal to n pi over L squared. So x, again C1 0, is equal to C2 sine of n pi x over L. And this is our solution for x. Next, we need to solve our second ordinary differential equation for t. So we have t double prime plus a squared lambda t equals 0. And the lambda we're going to use is this lambda here, because really it's the same lambda, right? So this lambda here is what we're going to use for this lambda when we're solving for t. So solving this differential equation for t double prime, our characteristic equation is r squared plus a squared lambda is equal to 0, which is r squared is equal to minus a squared lambda. And again, plugging in for lambda, I'm going to get that r squared is equal to minus a n pi over L squared. So that means r is equal to plus or minus I a n pi L. And when the characteristic has imaginary roots, the solution we get is a constant times cosine of our, and I rearrange these terms, n pi a over L times our variable t, plus a constant times sine of our an pi over L times our variable t. And notice I also used constants k1 and k2 because I already used c1 and c2 constants here when I was solving for x. So this is our solution for our ordinary differential equation for function t of time. To solve for the constants k1 and k2, I need to use my initial condition that t prime of 0 is equal to 0. So here I have the calculation for t prime. I have because we're taking the derivative of cosine, I need a negative, k1. Taking the inverse of this, we have L over n pi a, sine of n pi a over L times t plus k2, and then our L over n pi a, cosine of n pi a over L times t. Plugging in 0 for t, setting that equal to 0, I get minus k L n pi a sine of 0, so this goes away to 0, plus k2 L n pi a cosine of 0, which is equal to 1. So that tells me that k2 is equal to 0. And here I've rewritten my solution. And so the next step is that u is equal to our function x that we have here times our function t that we have here, keeping in mind that k2 is equal to 0. I don't know why I wrote this all out with k2 equals 0, and I didn't write c1 here and say c1 is equal to 0, but you'll just have to put up with my inconsistencies. But u of xt then is equal to our sine of n pi L times x times our cosine n pi a over L times t. So this is our fundamental set of solutions. So we get this for every value, for different values of n, we get a solution. So the general solution is a linear combination of all of our fundamental solutions. So we sum over n all of our solutions. To solve for Cn, the coefficients in front of each fundamental set for a particular value of n, so to solve for Cn, then we need to use another initial condition. And the initial condition we want to use is right here. At t equals 0, u of x 0 is equal to f of x. And so remember, we have solved for x, and we use the boundary condition that are at x equals 0 and x equals L, that these two are fixed at 0. but we haven't used this initial condition yet that says that at time t equals 0, there's some sort of initial displacement given by f of x, because right, the initial displacement depends on where you are on the string, so t equals 0, but the initial displacement, it might be that you pull the string up at this point, but then, even if you pull it up to here, the other points on the string is going to be different. So it's given to you by this function f of x. So that is exactly what we're going to use for our initial condition to solve for these c of n. So plugging in u of x is 0, again here, we're looking at time t equals 0. That is going to be by this formula, the summation from n equals 1 to infinity, cn sine of n pi l, and x is still x, right? It's t that's equal to 0, times cosine n pi a over l times t equals 0. So this is just cosine 0. So what we get is u of x0 is equal to the summation from n equals 1 to infinity, c of n sine of n pi l times x. And that's equal to our f of x, our initial displacement function. But if you look at this, what this is telling us is that Cn is our coefficients for our f of x written as a sine series, as a sine Fourier series. So Cn is going to be equal to 2 over L, 0 to L f of x sine of n pi L over x dx, because this is how you get the Fourier sine series. So that means the solution to our equation is going to be our Cn times sine of n pi L over x, cosine of n pi A L times t, where Cn is the Fourier sine series of f of x. Or rather, Cn are the Fourier coefficients of the sine series of f of x. And I also used the formula for the sine series where you just do the 2 over L, integrate from 0 to L. Or you can integrate 1 over L from negative L to L. Either one is fine. So what we have just done is we've derived the solution equations for the problem of the elastic string with non-zero initial displacement and zero initial velocity. Some comments from the solution. So for a fixed value of n, the solution u of xt is periodic with frequency n pi a over L and period 2L over NA. The natural frequencies n pi a over L are the natural frequencies of the string and the frequency at which the string will naturally vibrate. The natural mode over here, the sine n pi L times x, is the displacement pattern occurring when the string is executing vibrations at the given frequency. Each displacement pattern is called a natural mode of vibration and is periodic in the space variable x. The wavelength, the spatial period, this 2ln of the mode frequency, n pi a over L, is the wavelength. So for example, when n is equal to 1, we get the frequency is equal to a pi over L. That's here in blue, a pi over L, and then the wavelength is equal to 2L. When n is equal to 2, we have frequency is equal to 2a pi over L. That's in green here. And our wavelength now is decreased to L. And when our wavelength is equal to 3, we have 3 pi a over L, which is over here in yellow. And our wavelength is now 2L over 3. So these are the fundamental modes of the vibration of an elastic string. And now we can do an example. So we can consider a vibrating string of length L equals 30 that satisfies the wave equation. Here we have a squared is equal to 4. So 4u second partial derivative with respect to x is equal to u second partial derivative with respect to t. And we have x going between 0 and 30, that's L. T is greater than 0. Assume the ends of the string are fixed and the string is set in motion with no initial velocity. So that's exactly the problem we've been looking at. So we have 4u second derivative, partial derivative with respect to x is equal to u second partial derivative with respect to t. X goes from 0 to 30. T is greater than 0. And then for t is equal to 0, we are given that f of x, the displacement, is equal to x over 10 for x between 0 and 10, and 30 minus x over 20 for x between 10 and 30. So we want to define the displacement function u of x, t, of the string and describe its motion through one period. Here I have a squared is equal to 4, so a is equal to 2 and L is equal to 30. Now I could go and derive the solution kind of from scratch, but since I already did this for the general solution, I'm just going to use our equations. So my solution is going to be of the form Cn sine of n pi over L times x cosine n pi a over L times t, where our Cn is given by this integration here. So I'm going to start by integrating or finding my Cn. So that's 2 over L, again L is equal to 30, and then I can go from 0 to 10, x over 10, and then that's from our f of x, and then sine of n pi over 30x dx. Plus, then I have to do the integral from 10 to 30. And again, it's still 2 over L, L is equal to 30. And our function f of x here for x between 10 and 30 is equal to 30 minus x over 20 times sine of my n pi over 30x dx. So for both of these, I will need to use integration by parts. I'm not going to go over all this integration because it's actually not that interesting. I'm sure you know how to do this, but remember the idea of integration by parts is u gets broken down to something simpler, u prime. The v kind of toggles back and forth between sine and cosine, which is why we choose u to be our x in this case, or our 30 minus x. So here I choose u to be x, or x over 10, except I just kind of factored out the 10. So u is equal to x, u prime is equal to 1, and v is equal to my sine n pi over 30x. That's v prime. So v is equal to negative 30 over n pi cosine of n pi 30 over x. Here my u is going to be my 30 minus x, so my u prime is equal to negative 1. And here I plugged in to my formula. And so this first line here corresponds to the 0 to 10. And the second line here corresponds for my 10 to 30. And one thing I'm going to say, the hardest part about doing this integration by parts is really just keeping track of this coefficient 2 over 30 and making sure I keep multiplying both this part of the equation, the u times v, as well as my new integral by 2 over 30. And we keep adding more and more coefficients in front. So just make sure you keep multiplying by your coefficients and keeping track of your negative signs, because here's a negative, and then every time you do the derivative you might have a negative. So honestly, that's like the hardest part I felt like about this integral, and I actually had to do it a couple times because I kept making algebraic mistakes. But here you go. We finally get to Cn is equal to 9 over n squared pi squared sine of n pi over 3. And I'll let you take a look at this integration. And so what I get is u of xt is equal to my Cn, which I had solved as being 9 over pi squared. My n needs to go into my summation, so n equals 1 to infinity, 1 over n squared. That's where this came from. And then my sine of n pi over 3. So this much here is my Cn. And then I also need my sine of n pi over L times x. And then my cosine of n pi a over L times t. So remember that this u of x, is a function of x and of t. And here I have plotted u versus x. Later I'll plot u versus t, but I picked some values of t. T equals 0, 4, 7.4, 1, 11, and 15. So here. And honestly, you probably have some nice software package, hopefully, to do these plots for you, where you can just put in this equation, it'll plot. And because I'm working on my iPad and sometimes I'm traveling, what I have often is Excel, which is not exciting at all and sort of painful, but you really can plug this into Excel if you have nothing else to get these plots. And here I chose different values of t, so I plugged in t equals 0, and then I graphed x versus u of x 0. And that was this blue graph, and then I plugged in t equals 4, and I plotted x versus u of x 4. That was this green graph, and you can see I have other graphs as well. And things to notice that the maximum initial displacement is positive and occurs at x equals 10, while at t equals 15, which is half a period later, the maximum displacement is negative and occurs at x equals 20. The string then retraces its motion and returns to its original configuration at t equals 30. And this graph is kind of nice because it's kind of a picture of the string at different points in time. So here we have the string going from 0 to 30, and at t equals 0, we displace about a third of the way through, right? Because x goes from 0 to L equals 30. So about a third of the way along the string, we displace it up to u equals 1, right? And then when we let go, you can see what happens to the shape of the string as t goes to 4. And as t goes to 7.5, t equals 11. At t equals 15, that's when you get this maximum displacement in the negative direction. By the time you get to t equals 30, you come back to its original configuration, t equals 0, because of the period is equal to 30. And next, I plotted u versus t for values of x equals 5. So I got this red graph for x equals 5 when I plotted u of t 5 versus t. And then I did the same for x equals 10, holding x constant at 10. And then x equals 15 and x equals 25. So what this graph tells us is the motion is periodic with period equals 30 and illustrates each point remains motionless for a substantial part of each period. So for example, at x equals 10, so that's, if x, the string is of length L equals 30, that means x equals 10 is a third away along the string. This is the motion of the string, and what we see is it spends a lot of time here at negative, a little more than 0.5, so let's just say negative 0.65 or something, and it spends a lot of time over here close to 1, let's just say 0.8. So this point along the string, a third of the way through at x equals 10, it spends a lot of time down here at negative 0.6, did I say? And it spends some amount of time over here at 0.8. Right? So here at x equals 15, we're halfway along the string. So this point then seems to go between something like maybe 0.8 and 0.5. So this point here goes down to 0.8, and then it comes up to, 0.5 or 0.6 or something. So that's where this point, halfway along, spends a lot of time. And you can see it spends a lot of time motionless as opposed to moving here in between. Same with x equals 10, x equals 5, which is the motion of the point here going up and down, and x equals 25 is something over here close to 30 going up and down. Here I have the two graphs on the same page. If you have a fancy grapher, is that what it would be called, an application, a graphing application, you can do a three-dimensional graph, but I am going to skip that because I'm stuck with Excel. Unlike the solution for the heat conduction equation, which I've written here, the solution's here for your reference, this negative exponent here approaches 0 rapidly, which was what ensures the convergence of the series solutions. But the wave equation, it doesn't have anything that's exponentially decreasing. In fact, it just has a bunch of terms that, or not terms, but factors that oscillate. And they do not decay with increasing n, these factors here. So if the series does not converge, however, it does not necessarily mean the series for u of xt is incorrect, but only that the series cannot be used to calculate the second partial derivative xx and second partial derivative u tt. So we're going to establish the validity of the equation, our solution, over here, indirectly, looking at what the requirements are to be able to calculate these second partial derivatives. So here I've rewritten our solution to the equation, and again we're going to look at convergence and validity of the solution. To look at when these second order partial derivatives here, u, xx, and utt, are valid, we're going to look at another form of this equation. So we're going to rewrite u of xt as 1/2 h of x minus at plus h of x plus at, where h now is going to be f of x for x between 0 and L, and minus f of minus x from x between minus L and L. And I want to remind you something about f of x. So f of x is our initial condition when t is equal to 0. In other words, it's the position of the string in relation to x. So for this value x, the string might be up here. For this value x, it looks like the string might be here. So again, it's the initial condition t equals 0 where each point of the string is. And when we were solving for u of xt in general, first we solved for x using the boundary value conditions, and we got x is equal to this. When we solved for time t, we subject to initial conditions, we got this function here. And also I should say that we found that k2, this constant here, was equal to 0. So u of xt was equal to a function of this form. And then we took our linear combination to find the general solution, and then we said, okay, we want the initial condition when we used t is equal to 0 would be equal to f of x. So when t is equal to 0, this became cosine of 0, which is 1. So what we got is un of x0 is equal to the summation of cn sine of n pi x over L is equal to f of x. And so what we had from f of x is that f of x was the sine series, could be represented by a sine series. So here, h of x is an odd extension of that sine series f of x. Keeping that in mind, so h of x has the Fourier sine series, which is equal to cn sine of n pi L over x, or times x. So when we look at h of x minus t, so now I'm just going to plug in x minus t for x over here, and we get cn sine of n pi L x minus a over t, which using this formula here for sine of theta minus phi is equal to sine of theta cosine phi minus cosine theta sine phi, I can then rewrite this expression here as sine of n pi L x cosine of n pi a over L t minus cosine n pi L x sine of n pi a L t. Similarly, I can use the same way, the same cosine sine identity, trig identity in h of x plus at, and I get this expression here. Now when I add the two together and then divide by half, you will see I will get exactly what I have for u of xt. So again, in other words, I can rewrite u of xt in this form here, where h of x is an odd extension of f of x. And where does that leave me? Well, it's easier to look at this function here and talk about where this is continuous and where you can take derivatives. So to calculate here the second derivative, partial derivative with respect to x and then x, as well as the partial derivative of u with respect to t and then t, we must need u of xt to be continuous, which requires h of x, where's h of x? Here. We defined it here to be continuous from infinity to infinity, which requires f of x to be continuous on the original interval, 0 to L. And u of xt needs to be twice differentiable because we have this uxx, which requires f and f prime to be continuous on the interval 0 to L. And since h double prime is the odd extension, we also need the f double prime of 0 and f double prime of L is equal to 0. So these are the three requirements that we have in order to take these second order partial derivatives. If some of the continuity requirements and any of these three are not met, then u of xt is not differentiable at some points in the strip 0 to L and t is greater than 0, and thus is a solution of the wave equation only in a somewhat restricted sense. But here again, we have our three conditions in order to calculate these derivatives and for this solution, this form of the solution to make sense. But enough of that. We're going to go ahead and do another example. Consider an elastic string of length L whose ends are held fixed. The string is set in motion with no initial velocity. From an initial position, u of x0 equals f of x. Find the displacement u of xt, plot u of xt versus x for values of t between 0 and 20. I'll also plot u of xt versus t, and then describe the motion of the strings in a few sentences. So this is my f of x here. And I put my relevant equation up here. I have the general form of my solution here, and I also have that Cn is equal to 2 over L, and then using my f of x, I pulled out my 1 over L cubed right away. The integral from 0 to L, 8x, L minus x squared, again I already pulled out my L cubed, times my sine of n pi over Lx dx. I pulled out my 8, so I got my 16, multiplied these L to the 4th, so I still have the integral 0 to L. I have my x, I squared my L minus x, and then I have my sine term. This here, I guess I went ahead and did some expanding. I multiplied by x. So this here I had to do with integration by parts. And again, the idea of integration by parts is when you take u prime, it should get simpler, whereas v can go back and forth. So v is my sine term, my v prime is my sine term, and v is equal to a cosine term. And then my u is this, my L squared x minus 2xL plus x cubed. So you can see my u term has an x cubed term, whereas my u prime gets simpler because it becomes x squared. I plug this into my formula. I have my 16L over 4, and then I have my u times v. So here's u, and here's v, and I need to evaluate that between 0 and L. And just looking at this really quickly, when I plug L into here, I get L cubed minus 2L cubed plus L cubed. So this goes to 0, and when I plug in 0, this factor is going to 0. So this term goes completely away. So I'm then going to subtract my integral v u prime. So here's my 16L to the 4th, and one of the biggest mistakes I make is first not keeping track of my negatives because there are negatives being thrown around everywhere, and also forgetting to multiply my integral by this constant. But here I have it, minus 16L over 4, and then I need v times u prime. So u prime is my L squared minus 4x plus 3x squared, and my v is equal to my minus L over n pi cosine n pi L x dx. So you can see this, I can pull this out and become positive. But here again, I need to use integration by parts again. I need to keep using integration by parts until I get rid of this x. But anyway, you can see that now my u term, where here it has an x squared, my u prime gets a little bit simpler because now I only have an x term. I plug in my formula and I see again this term goes away, my integral stays, and then because I still have this x term, I need to do one more integration by parts, which I do here. Now this part does not go away, but I can plug in, and eventually, but I do see that this will go away when I plug in L here. This will become sine of n pi, which is 0, and sine of 0, which is 0. So this term goes away. So now I can evaluate. I tried to do this calculation here in my head, but I guess I just couldn't, I'm not up to the algebra. So I did write it all out, and eventually I got 32 over n pi cubed cosine of n pi plus 2. And remember, this is the answer for Cn. We haven't quite gotten u of xt yet. But here I wrote u of xt. Here is my Cn, and here is the rest of my formula, my sine of n pi Lx, and my cosine n pi a over Lt. And I did some graphs. Again, I use Excel, which is like not anything to brag about, but that's what I have. So I did u versus x. So over time, this is what the graph looks like. It's like a snapshot of the string at time t equals 18, t equals 4, t equals 7. Whereas here, it shows you what each point does. So like at the halfway point, that would be x equals 15. I don't have x equals 15. But at x equals 1, you can see where the point very close to the left boundary, how it moves in time. This over here, x equals 6, that's 6 over 30. So 1/5 of the way on the string, you can see how that point moves in time. So the flow is smooth and continuous, and the pictures are smooth, and and the peaks are smooth, as you can see, and they do not occur in the middle. I am going to do another example, very similar, same function here, but now I'm going to consider an elastic length L, the same, whose ends are held fixed. The string is set in motion from its equilibrium position, so now f of x at 0 is 0, but the initial velocity now is equal to g of x. So in the previous problem, this function here, this 8x L minus x squared over L, was f of x, the initial position, but now it's initial velocity. And here I have the relevant formula for non-zero initial velocity for your reference here. And if you look at it, it's really strikingly similar to the formula for c of n, because c of n is just f of x times sine of n pi over Lx. So this part of the integration will be the same. You'll be using integration by parts and it'll be exactly the same. The difference is this coefficient in front. And as I mentioned again, I did this whole integral all over again. I don't know, as an exercise, and I'm not sure what. Frustration? I don't know. But anyway, and I did use integration by parts 3 times. I plugged it in. Again, I couldn't do this in my head, so I wrote it all out, and I eventually get 32L a n pi over 4 cosine of n pi plus 2. And again, this shouldn't surprise me. This should come out to be the same because this formula is the same as for Cn. What's different is this coefficient out in front. And here we have the final solution for u of xt. This is my last example. Here are some notes from my first overview slide that will be relevant. So our example is we have a steel wire 5 feet in length stretched by a tensile force of 50 pounds. The wire has a weight per unit length of 0.026 feet per pound. Find the velocity of propagation of transverse waves in the wire. Find the natural frequencies of vibration. If the tension in the wire is increased, how are the natural frequencies changed? And here is the solution. So we have L is equal to 5. T, the tensile force, is 50 pounds. The mass per unit length is 0.026. And something I should mention is rho should be in slugs per feet. So we're going to have to divide this mass per unit length by 32.2. So a squared over here we see as t over p, and we also have noted that a is a velocity. So a squared is equal to 50 over our rho, which gives us a is equal to 248 feet per second. And again, this is the velocity of the propagation of the wave. Our natural frequencies here is equal to n pi a over L. So I have n pi, and then I have a over L. So our a is here, and our L is 5 pounds. So we get 49.8 n pi radians per second. This is the natural frequency. And changing the tension, here if we look at the natural frequencies, we can look at the natural modes. They will not change the natural mode or the natural frequencies, since natural mode does not depend on t. To review what we discussed in this video, we talked about the wave equation, and we motivated the wave equation by looking at vibrations on an elastic string. We suppose we have an elastic string of length L, tightly stretched between two supports at x equals 0 and x equals L. We suppose that the string is set in motion so it vibrates in the vertical plane. And let u of xt denote the vertical displacement experienced by the string at a point x, that's away from x equals 0, and at time t. So if dampening effects such as air resistance are neglected and amplitude of motion is not too large, then u of xt satisfies the second order differential equation a squared u xx equals utt. And we did not derive this equation, but it is done so in the appendix of your book. What we did derive was the solution to the wave equation. But going back just to look at this wave equation here, we have that we will be given this differential equation, second order differential equation, and then we also have the boundary values, these boundary conditions. So at x equals 0 and x equals L, these 2 points remain fixed at 0. The height of the displacement is 0 at the boundaries. So that's our boundary values. And then here we have an initial position. So if we if we displace this initially, we have u of x0 at time 0 is equal to f of x, and f of x can be equal to 0. So this is our initial position, and we also have a potential initial velocity. So at t equals 0, we might take the first derivative of u with respect to t, and we will get a function telling us how fast each point along the string is going at time t equals 0. So this problem governs transverse waves, water waves, acoustic waves, electromagnetic waves in the atmosphere, elastic waves in a solid body. There's a two-dimensional version and a three-dimensional version here, right? We're only looking at vertical displacement, so we have a one-dimensional version. We have other formulas here for the period and the frequency of this wave, as well as natural frequencies, natural mode. And also I should mention that when we calculate rho, it needs to be in slugs, which we did an example where we calculated this rho. Once we have this wave equation with the boundary conditions and initial values, initial position and initial velocity, we then worked at solving this equation. And first we looked at non-zero initial displacement, where f of x is non-zero, but we have an initial velocity equal to 0. And we got this as our solution here. And then second, we looked at non-zero initial velocity. So we set f of x equal to 0, so the initial displacement is 0, but we have an initial velocity, g of x, and we got this solution here. The general problem for the elastic string, where we have both initial velocity and initial displacement, is just found by adding these two solutions together. Using superposition, we can add the two solutions together. And that is it for this video. Thank you for watching.